Welcome back to our deep dive into the OEIS.
Yeah, it's always exciting to jump into these sequences.
You can say that again. Today we're taking a look at A000143.
Ah, yes, the sums of 8 squares.
It sounds simple enough, right? Just adding up squares.
Well, it starts off simple, but trust me, it gets interesting.
I bet. So for our listeners just getting started with this sequence.
Yeah, for those who are new to A00000143.
What exactly are we dealing with here?
So this sequence, it lists the number of ways.
Okay.
The number of ways to do what?
To represent any non-negative integer.
Like 0, 1, 2, and so on.
Exactly as the sum of 8 squares.
8 squares, that's a lot of squares.
It is, and there's a twist.
Okay, what's the catch?
Both the order and the signs matter.
So it's not just about the final sum.
Right, it's about the arrangement too.
Can you give us an example?
Sure, so let's say we have 1, 100, and 0, 0, 0, 0.
Okay, 8 numbers there.
Now that's a different representation from 0, 1, 1, 0, 0, 0, 0.
Oh, because the ones are in different spots.
Exactly, even though the sum is the same. Interesting, so the position makes a difference.
It does, and the signs too.
You mean like using a -1 versus a +1?
Exactly, like -1, 2 plus 12 is different from just using 2 positive ones.
So we're being very specific about how we add these squares.
Absolutely, and that attention to detail leads to fascinating observations.
Like what? What kind of patterns do we see in this sequence?
We'll take a 0, the very first term.
The number of ways to represent 0 is a sum of 8 squares.
Right, well, all 8 squares have to be 0 to sum to 0.
So there's only one way to do it.
Exactly, making a 0 equal to 1.
Makes sense. It seems like a simple starting point.
Now let's jump to A1.
Representing 1 is a sum of 8 squares.
We have 8 positions to place a 1 or a -1.
And for each position, there are 2 sign choices.
So we have 8 times 2.
Which gives us 16 possibilities.
So A1 is 16.
Okay, I'm starting to see how the number of possibilities increases.
And it gets bigger quickly. A2 jumps all the way to 112.
Wow, so things escalate pretty rapidly.
They do, which is why we have a computational formula.
A formula to help us calculate these values.
Exactly. It's a systematic way to find AN for any n.
I'm curious, what does this formula look like?
It's AN 16 -1 2 1n d minus 1 d d3.
Whoa. Okay, that looks a bit intimidating.
It might seem that way at first, but let's break it down.
I'm all for making complex things easier to understand.
All right, so let's focus on the summation first.
The part with the sigma symbol.
Yes, that's the sum dn d0 -1 d d3 part.
What does all that mean?
It means we're summing over all the positive divisors of n.
Okay, so if n is 2, its divisors are 1 and 2.
Exactly, and for each divisor we cube it.
Okay, so for 1 we get 1 cubed, which is just 1.
And for 2 we get 2 cubed, which is 8.
Right, and then what do we do with those cubed divisors?
We multiply each one by -1 raised to the power of that divisor.
So for 1, it would be -1, 1, which is -1.
And for 2, it would be -1, 2, 8, which is +8.
Okay, so we have -1 and 8, and then we add them together.
You got it. So for n is 2, the sum would be -1 plus 8, which is 7.
So we've tackled the summation part. What's next?
Now we multiply that sum by 16 and by nepling 1n,
So for n equals 2, that's 16 equals 1 to 7.
which simplifies to 112, exactly what we got before.
Wow, so those alternating signs and cube divisors really do work together.
It's pretty neat, right? It shows the elegance of number theory.
Definitely. And it gives us a way to calculate an for any n.
Exactly. It's a powerful tool, especially when n gets large.
So we've got this formula, but you mentioned there's another way.
Ah, yes. We can also express the sum using sigma notation.
You mean like 3n even? 3n odd.
You got it. This represents the difference
The difference between what?
between the sums of cubed even divisors and cubed odd divisors.
Okay, I think I'm following you.
So 3n even is the sum of the cubed even divisors of n.
And 3n odd is the sum of the cubed odd divisors.
Exactly. This can be a more efficient way to compute the values.
Especially for larger numbers, I imagine.
You're right. It simplifies the calculation quite a bit.
It's fascinating how there are multiple paths to the same result.
It's one of the beautiful things about math, wouldn't you say?
Absolutely. But speaking of different paths, you also mentioned a generating function.
Yes. The generating function for this sequence is theta 3q8.
Theta 3q8. Now that sounds even more complicated.
It might look that way, but the key is the Jacobi theta function.
A function within a function.
In a way, yes, it's a fascinating function found in advanced number theory.
So our sums of squares sequence connects to some pretty high-level math.
It does. It shows how interconnected math can be, even from simple concepts.
Like those Russian nesting dolls, open one and there's another inside.
Exactly. And in this case, A000143 is one of those outer dolls.
Leading us to these deeper concepts like modular forms and theta functions.
Precisely. But for now, let's focus on another interesting aspect.
Okay, what else is there to explore with A000143?
Well, there's the multiplicative property of this sequence.
Multiplicative property, what's that all about?
So we can express an as 16bn for any n greater than or equal to 1.
Okay, so we have this new function bn.
Right, and what makes bn special is that it's multiplicative.
Meaning what, exactly?
It means if you know the value for prime powers.
Prime powers, like 2 squared, 3 cubed, and so on.
Exactly. You can easily calculate bn for any number.
So knowing the value for prime powers unlocks everything else.
In a way, yes, it simplifies the calculation tremendously.
And how do we find the value of bn for these prime powers?
We have specific formulas for that depending on the prime.
Different formulas.
Yes, for odd primes, it's BP. Yeah, P3e plus 3, 1, P31.
Okay, and what about for the prime number 2?
For 2, it's B2e, Q3e plus 3, 1, 7, 2.
Those look a bit complicated.
They might seem that way, but they make calculations much easier.
Especially when dealing with large numbers with many factors, I imagine.
You got it. Let's try an example, shall we?
Sure. How about we calculate A2 again using this method?
Perfect. So first we need to find B2.
Since 2 is a prime number, we use the formula for P2.
That's right. So B2e, 2, 3e plus 3, 1, 7, 2.
And in this case, E is 1.
So B2, 26, 1, 7, 2, which simplifies to 7.
All right, so we have B2 is 7. Now what?
Now we simply multiply that by 16 to get A2.
So A2 equals 16, 7, which is 112, just like before.
Exactly. It's amazing how it all comes together.
It is. And prime numbers seem to play a crucial role again.
They truly are the building blocks of number theory.
This multiplicative property gives us another way to navigate this sequence.
It does, and it hints at the deeper structure underlying A000143.
I'm definitely intrigued to learn more.
Well, there's much more to uncover. Join us in part 2 to delve deeper.
We'll unravel the secrets of modular forms and theta functions.
It's going to be a fascinating journey.
I can't wait.
Welcome back to our deep dive.
I'm ready to explore more of this sequence.
Great. We left off talking about modular forms and theta functions.
Those are some pretty advanced concepts.
They are, but we can understand them without getting too technical.
Okay, I'm all ears.
All right, so imagine a kaleidoscope.
With all its colorful patterns.
Exactly. Now imagine turning it.
The patterns change, but there's still symmetry.
Right. That's kind of like a modular form.
Instead of physical rotations, it's mathematical transformations.
Precisely. These forms have a remarkable degree of symmetry.
So even as they transform, they maintain a certain structure.
You got it. They're well-behaved under these transformations.
And what makes these well-behaved functions so special?
They have profound connections to prime numbers.
Prime numbers always seem to pop up in number theory.
They do, and they're also connected to elliptic curves.
Elliptic curves, I've heard of those, but don't really understand them.
They're fascinating objects with lots of applications.
Maybe a topic for another deep dive.
Definitely. But for now, the key is that our generating function.
The one for A000143?
Yes, it's related to these modular forms.
So by studying this sequence, we're indirectly exploring these forms.
Precisely. It highlights how interconnected math can be.
It's like opening a door to a whole new world of concepts.
That's a great analogy. Even simple concepts can lead to deeper ones.
Now, what about those theta functions?
Ah, yes, they're a special class of functions.
How are they related to modular forms?
They're closely related, often appearing in similar contexts.
Okay, and where do these theta functions typically show up?
One area is problems involving lattices.
Lattices, like a grid of points.
Exactly. Theta functions help us understand their properties.
So they provide insights into these geometric structures.
They do, both geometrically and arithmetically.
Interesting. And what kind of applications does that lead to?
Well, lattices appear in various fields.
Like what?
Crystallography, for example, and coding theory.
So they bridge the gap between abstract math and real-world applications.
You could say that. Now remember that generating function.
The theta 3q8.
That's right. Well, the theta 3q is a specific type of theta function.
It has a special name, doesn't it?
It's called the Jacobi theta function.
So we're essentially studying a Jacobi theta function to the 8th power.
Precisely. It's all connected.
This is blowing my mind a bit, but I love it.
It's exciting, right? to see these connections unfold.
Definitely. Now, for our listeners who are number theory students,
Yes, those who are interested in exploring further,
what advice would you give them? Where should they go from here?
I always recommend a solid foundation.
What kind of foundation are we talking about?
Diving into classic number theory texts.
Are there any specific books you'd recommend?
Absolutely. Hardy writes An Introduction to the Theory of Numbers.
A classic, for sure. Are there specific chapters they should focus on?
The chapters on quadratic forms and theta functions.
Okay, those sound particularly relevant to our discussion.
They are, and of course the OEIS itself is an amazing resource.
For A000143 specifically.
Yes. The entry for A000143 is packed with information.
Formulas, references to other sequences, links to research.
It's all there. A treasure trove of knowledge waiting to be explored.
I'm definitely going to spend some time on the OEIS website later.
You should. It's a fantastic tool for mathematical exploration.
Any other suggestions for our aspiring number theorists out there?
Connect with others. Online communities and forums are great.
You mean places where number theory enthusiasts gather?
Exactly. Sharing ideas, asking questions, it can be incredibly helpful.
It's inspiring to think about this network of people exploring these ideas.
It is. It's a reminder that math is a collaborative endeavor.
I'm even more excited to keep learning about A000143 now.
That's great to hear. And there's still more to uncover.
Right. We still have part 3 of our deep dive to go.
We'll wrap things up with some final thoughts and intriguing connections.
I can't wait. Welcome back to our deep dive. It's time to wrap up our exploration of OEIS sequence A000143.
Yes, the sums of 8 squares. It's been quite a journey.
It has. We've covered so much ground from basic calculations to advanced concepts.
It's amazing how much we've uncovered, wouldn't you say?
Absolutely. From those initial examples to modular forms and theta functions.
It's a testament to the richness of number theory.
Even seemingly simple ideas can lead to such profound insights.
Exactly. So as we conclude this deep dive, let's highlight some key takeaways.
That sounds good. What are some of the things that stand out to you?
Well, first, A000143 exemplifies how a simple problem
Like counting the ways to some squares.
can open doors to a deeper mathematical understanding.
We saw how this sequence connects to modular forms and theta functions.
Concepts with applications far beyond this specific sequence.
It's a reminder that math is interconnected, even seemingly unrelated areas.
Exactly. Exploring one concept often leads to links with others.
It's like a tapestry of ideas all woven together. It makes you wonder what other connections are out there waiting to be found.
Definitely. There's always more to discover, even in familiar territory.
Speaking of discoveries, we also saw the power of generating functions.
Ah, yes, that mathematical tool that encapsulates so much information.
It's like a blueprint for the entire sequence.
Precisely. And the fact that it involves the Jacobi theta function.
Deepens the connection to those advanced areas we discussed.
It's like finding a hidden passage that leads to a whole new world.
And of course, we can't forget those intriguing patterns within the sequence.
Like the divisibility by 16, that's a fascinating one.
Every term after a 0 is divisible by 16. Why does that happen?
It points to a deeper structure, a hidden order within the sequence.
It makes you wonder what other patterns might be lurking beneath the surface.
There's always something more to uncover, isn't there?
Always. Now, for our listeners who are number theory students.
Yes. Those who want to delve deeper into A000143.
What advice would you give them for further exploration?
I'd say start with a solid foundation.
Like reading classic number theory texts.
Exactly. Hardy and Wright's book is an excellent resource.
And focusing on chapters about quadratic forms and theta functions.
Those would be particularly relevant for understanding the sequence.
And of course, the OEIS entry itself is a treasure trove of information.
Absolutely. It's a fantastic resource for anyone interested in sequences.
I'm definitely going to spend more time exploring the OEIS website.
You should. And don't forget the power of connecting with other enthusiasts.
Online communities and forums are great for sharing ideas and asking questions.
Exactly. It's a collaborative field, and learning from others is invaluable.
So as we conclude this deep dive, what's one final thought you'd leave us with?
I'd say this A000143 is just one example of the beauty of integer sequences.
There's a whole universe of patterns, connections, and surprises waiting to be discovered.
Keep exploring, stay curious, and embrace the wonder of mathematics.
Beautifully said. So to our listeners, thank you for joining us on this journey into A000143.
It's been a pleasure exploring this fascinating sequence with you.